Hello, this is Desmond Parker with A Plus College Ready. Today we'll be talking about chemical bonding. So, the question is, why do atoms form chemical bonds? And the simple answer to that is to stabilize the atom. By giving your atom a full outer shell of valence electrons, it lowers the overall energy of that atom, causing it to be more stable. And it also gives it an electron configuration that looks similar to or the same as the noble gases, which tend to be non-reactive. So overall bonding, when we are breaking bonds and forming new bonds in our chemical reactions, we have energy that is being either absorbed or released. So in breaking of bonds, we absorb energy, and when we form new bonds, we will release energy. And if you take a look at the graph here, you'll notice that the potential energy will go down as we have new bonds formed, and then it rises again when we have bonds that are broken. So we have two types of general forms of bonding. The first type we're going to talk about, well, actually there are three. The first type we're going to talk about is covalent bonding. With covalent bonding, we are sharing valence electrons, and typically your atom is trying to get 8 electrons in its outer shell. Now there are some exceptions to this rule, such as hydrogen, boron, lithium, and beryllium, and there are actually a lot more exceptions to the rule than the ones that follow. Any atom that has a d orbital has the capacity to hold more than 8 electrons. So that's typically elements phosphorus and beyond, which will tend to do that. With our covalent bonds, we have two particular types. We have nonpolar covalent and polar covalent bonds, and you can see the electronegativity differences between those. So our electronegativity, just in case you've forgotten, is the propensity of an atom to attract a bonding pair of electrons. So the higher the electronegativity value is, the more it wants electrons, and the lower that electronegativity value is, the less likely the atom wants to attract electrons. So you can just simply subtract the difference, and whatever the difference between those are represented here by these values over on this side. So let's take a look at a quick example. So we have a nitrogen-nitrogen bond. Well, our nitrogen has a electronegativity of 3.0, and our other nitrogen has an electronegativity value of 3.0. So you're going to take these two and subtract these two values from each other, and you're going to take the absolute value, and that gives us 0. So it tells us that that molecule is perfectly nonpolar. Now, on the other hand, we'll have molecules such as CO2, which looks like this. If we were to take the electronegativity difference of these two, we'll actually see that we will have a polar bond. So oxygen is 3.5, and carbon is 2.5. And if you take the absolute value, you get 1.0. But because we have electrons going this way and electrons going this way evenly, we will actually have a nonpolar molecule. So the bonds themselves are polar, but the molecule is not. And that's because of the symmetrical nature of CO2, which you will actually learn about that a little bit later on when you get into molecular geometry and intermolecular forces. So these polar bears and penguins are a perfect example of what's going on when we have these nonpolar molecules. So the penguins are both equally strong with each other. So when this arm wrestle competition, neither one of them are going to win. And that's the same thing that's going on with the two polar bears, which are represented by chlorine. Again, this arm wrestling competition they have, because they are both equally as strong, they will not win the battle. So that goes back to our electron sharing. Whichever one is the strongest will get the electrons, but since both of them are equally as strong, they both will share the electrons equally. Now back to what I was saying about our bonds being polar but our molecule being nonpolar. Our penguin, which represents the carbon, and the polar bears, which represent the oxygen, are both attracted to that ice cream. So since the penguin is holding on to that ice cream, and the polar bears are on either side, they have a equal pull on that central penguin or carbon atom. Now with our polar covalent bond, this is when we have an unequal sharing of electrons. So the atom that is most polar, or the one that is most electronegative, will be the one that holds on to the electrons longer than the one that is the least electronegative. So again, you have some molecules which have nonpolar bonds, but due to their geometry will be polar. So ozone is a perfect example of that, O3. It has a slightly bent shape to it. Let me draw that out for you. And due to that slightly bent shape of the ozone molecule, the overall molecule is polar. So one of the exceptions to this rule tends to be molecules that consist of just carbons and hydrogens. Typically they have these very, very long chains, and eventually everything kind of cancels out with each other, so that molecule overall might be slightly polar, but we just consider them to be more non-polar than anything. Now back to our penguins and polar bears example. In this case right here, we have this polar bear, which is represented by a fluorine atom, and our penguin, which represents the hydrogen atom. That polar bear is much stronger than that penguin, so it's going to have that ice cream much longer than the penguin will. And typically in real life, of course, we know this would not happen because the polar bear would more than likely eat the penguin. Ionic compounds. This is when we basically steal electrons. So we have an atom which is so electronegative, and we have it paired with an atom which is not very electronegative. And that electronegative atom is strong enough to simply take the electron from the atom, like we have in this first example here. This electron right here is going to simply be stolen by the chlorine atom. So that's going to give the chlorine, or what we call now the chloride ion, a negative charge overall. And then the sodium is going to get a positive charge. And also notice that that outer shell on sodium is now gone. That is where sodium gets its stability from. So now it has 8 outer shell electrons, as indicated by the drawing here. And then chlorine also has its outer shell electrons as well, all 8 of them. So both of them actually get satisfied in this relationship. With ionic compounds, they form a lattice structure. So we don't simply have one sodium and one chlorine compound floating around. They're actually in this big block crystal called a lattice. And typically, the higher the charge of each of the atoms in the lattice are, the more energy it's going to require to break it. And then there's also the component of how big the atom is as well. So smaller atoms tend to be harder to break that lattice energy than larger atoms. So if you look at my example of sodium chloride and calcium chloride, both of them have the chloride ion. Sodium has a lower charge than the calcium does, so that means that calcium has a stronger hold on its chlorine atom. So it requires more energy to break that bond than it does for sodium chloride. This is why we say in non-biological systems that ionic bonds are much stronger than covalent bonds are. And typically, only water has enough energy to break these bonds. So, going back to our polar bears and penguins example, this polar bear just basically takes the ice cream from the sodium. That's what's going to happen. Now, here you have the penguin yelling, "Come back." Actually, in reality, the sodium really doesn't want that electron back because it makes the sodium highly reactive. So by that sodium losing the electron, again, it becomes much more stable. Now we have metallic bonding. These guys have what we call delocalized electrons. So these electrons basically are just floating through the metal system. And this is what allows electricity to be conducted. So we can apply a charge to one end and some place for that charge to come out on the other end, and those moving electrons are what helps move energy or move electricity from one place to another. So unlike our covalent and ionic compounds where these are locked with a specific atom, these are shared amongst a bunch of different atoms. So just taking a look at our periodic table here, this is typically how it's broken up. Most of the atoms that are on the periodic table are metals. We have a few what we call metalloids, which are, they're kind of behave both as a metal and a non-metal. And then we have elements that are purely non-metals. So some characteristics of our metals is they have luster to them, which means they shine. We can draw them into thin sheets. They're ductile, which is why we use them for wires. And then we also have high energy in order to get them to vaporize. So there is a lot of energy that has to be input into the system in order for the vaporization to occur. So you can see here on this graph right here that the melting point of zinc is at 692 Kelvin, and the boiling point is at 1100 Kelvin. If you take a look at the amount of energy needed to get this to a gas, it is extremely high, probably about 165,000 degrees Kelvin. So it requires a lot of energy. I'm sorry, not 165,000 degrees. At the 1100 degrees. That's what it takes to get it to a gaseous state. So let's take a look at some AP questions. So pause the video and go ahead and work through this one. So this question asks us to look at increasing bond polarity. So all we have to do is take the difference between the bonds of the different compounds. So we're not looking for whether or not the molecule is polar, we're looking for the bond is polar. So the first one is 0.4, second one is 1.2, and the third one is 1.5. So the tricky part of this is making sure that you give them what they want to. They want increasing bond polarity, so they want it from smallest to largest. Just so happens in the case that I gave this to you in smallest to largest. So it increases as it goes down. So that would leave us with answer A. So go ahead and pause this one and answer the question, and then we'll talk about it. All right, for this question right here, we're looking for the ones that have the largest, net charge difference, and we want to find the one that is the smallest atom. So sodium chloride and cesium. Sorry about that. So we're going to take a look at the one that has the biggest set of charges on them. So sodium chloride and cesium bromide, we are going to eliminate both of those because their charges are small. And then on top of that, cesium is a really, really big atom, which means that it is not going to have a strong force of attraction with the bromine. So that leaves us between calcium oxide and magnesium oxide. Magnesium is the smaller of the two, which means that it will have a stronger force of attraction with the oxygen, which will leave us with magnesium oxide as our final answer. And lastly, this is characteristics of crystalline solids. So go ahead and pause the video and we'll talk about it. Alright, so we're trying to find which of the following are the identity of a white crystalline solid. So immediately from this, I would eliminate copper, because copper, I would hope you would know that copper is not white. So since copper is not white, it cannot possibly be copper. It has a relatively high melting point and it does not conduct electricity as a solid, but it does in aqueous solutions. A would be the next one that I would eliminate because that is a covalently bound compounds. Covalent compounds do not conduct electricity. Only ionic compounds do when they are in solution. The only ionic compound, true ionic compound that we have up here is sodium hydroxide. Silicon dioxide, this is a covalent compound. Even though silicon is a metalloid, it is still considered a special category of covalent compounds called network covalents. And lastly, we have a sample of a hard binary solid at room temperature that does not conduct electricity as a pure solid, but conductive when dissolved in water. Go ahead, think about what type this would be, and we'll talk about it in just a moment. Alright, so we've only talked about 3 types of chemical bonding which occur. Hydrogen bonding, these are not bonds. These are forces of attraction, which we have not talked about yet, but I would hope that you would not have chosen that one simply because we had not talked about it. We should know that metals conduct electricity even when they are not in water, so I would hope that you would have eliminated metallic bonding. Sorry about that again. And then lastly, we should hopefully know by now that covalent bonding does not result in electricity being able to flow. So that will leave us with ionic compounds. Alright, I hope this video has been helpful for you. If you have any further questions, make sure that you forward them to your instructor. And again, this is Desmond Parker with A+ College Ready, and I'll see you soon.